now we just saw a nice presentation on the impact of 3D effects on fluxes and heating rates. And this presentation is more on the effect on the pixel level and on the cloud properties that we can retrieve with EarthCARE. So to start with the imager perspective, we use two channels to calculate the microphysical properties. Those are usually a visible channel and a short-wave infrared channel. The visible channel is more reflective and the short-wave infrared channel is more absorbing, as we can see. And also the scale is here on the half of the absorbing channel. So yeah, much darker compared to the visible. And then lookup tables are created from 1D radiative transfer simulations with various combinations of cloud optical thickness, cloud effective radius, and solar zenith angles. Those are stored, and then the real measurements are then compared to the lookup tables, and then we can retrieve the optical thickness and the effective radius. Yeah, and we can see, for example, the impact. So over here, the visible is much brighter. We get higher optical thickness. Here the reflectance is a bit lower optical thickness, and opposite then for effective radius. Here we see, oh, it's really dark, so we assume more absorbing larger particles, and therefore, yeah, higher effective radius for lower short-wave infrared. Now we assume 1D radiative transfer, but we live in a 3D world. So 1D radiative transfer, we just saw we have the independent pixel approximation, and we assume the clouds to be plane parallel and homogeneous. So in this example, we just saw also the pixel can't escape to the side. So yeah, no horizontal photon transport, and also other pixels which could block sunlight, for example, are not considered. And yeah, the 3D reality looks much different. We have a vertical variability of microphysical properties, as shown here for the effective radius, which changes throughout the columns. And we also have 3D radiative effects. Here I mentioned two of those. The horizontal photon transport. Here we see a simple sketch of a cloud. The outside is thicker and more reflective, and then the photons get redistributed due to the horizontal photon transport. So the thinner curved parts, which are darker, receive more photons than they get, and opposite for the other pixels. So we get a smoothing, and then we have also the example from the slide before. And now we look at the sun direction indicated by the arrows, and we see, okay, the front side of the cloud is much brighter than the back side. So we can assume that it's not caused by the microphysical properties of the clouds, but also from the cloud top structure, which is not considered in 1D. And yeah, this brings us to the questions. How can we identify 3D effects in imager measurements? And what is the impact on the imager retrievals? And how can we get from 3D to 1D-like radiances to get more accurate cloud retrievals, as cloud retrievals are calculated on 1D? And for this talk, we will focus on the side illumination and shadowing effects. So we can use the brightness temperature gradient as a simple proxy for this effect. So here we can see the axis, the pixel we are considering, and based on the solar azimuth angles or sun position, we can then identify front pixel and a behind pixel. And with the brightness temperature gradient reflecting the cloud top structure, we can then conclude how the cloud slope looks like. Now here two examples. If the front pixel indicates a higher cloud top, and then the behind pixel we have a slope tilted away from the sun, so a negative brightness symmetric gradient, and we assume to be a more shadowy area, and opposite then, and to get illuminated cloud hill. And yeah, here the example from before, we can see with the brightness temperature gradient, illuminated pixels, and right down. To get the truth, we have to rely on the model world as we don't have 1D in observation. So to test this method and see its limitations, we performed Monte Carlo case study based on an icon simulated case of the Hurricane Humberto, which was performed by Jan Kolja Wagner and Fabian Senn. And the 3D transfer was calculated with the Mystic transfer solver. And now looking at the visible reflectances of the solar channel, we can compare the 3D and the 1D, and we see the 1D is not as rough, and we see here the bright spots in the 3D, and for complementary reasons also the thermal channel, which can then be used to calculate the brightness temperature gradient on the right. And you can also have a look at the 3D minus 1D on the pixel level. And we can see it looks quite similar in some areas, in other areas not as much. We now have a closer look at this section on the bottom right to investigate further and look more into the details. Here we have again the 3D minus the 1D and the brightness temperature gradient. And we see also a slight limitation of the Monte Carlo. It's a bit noisy because we need really a lot of photons to produce a really smooth image, but it's definitely enough to evaluate and 3D rated effect. And here on the bottom left plot, we have the brightness temperature gradient from the left, with the more shadowy pixels to the right, with the illuminated pixels. And we can clearly identify the trend for the different height levels within this scene. And we also have reflectances that reach over 1. So this is already a good indication for 3D rated effects. And next to it, we have the 3D minus the 1D, and we can see that the slopes of the fits that I just show you look quite similar, and then based on the slopes of the reflectance in the 3D, we can then predict the 3D minus the 1D. Now in the corrected version, we have more symmetry, but still have high absolute values. So showing here the values, we have a quite low mean 3D minus 1D overall, but the absolute error is around 0.05 for the initial case, and after the correction we are still at 0.036. And so we can solve parts of the 3D radiative effect, but the method cannot predict it perfectly, and so there might be more effect related to the cloud top structure, and part is also attributed to the noise of the Monte Carlo. So we have two versions of the 1D radiative transfer, and we also see differences between those two. So variability is also a thing, and we also have other 3D radiative effects. And to disentangle which effects are from the cloud top and which effects are not related to the cloud top, we have performed the same Monte Carlo simulations, but just from the other sun position. So we have the initial sun position in the southwest, and we have performed another simulation for the northeast. And yeah, to explain the upcoming plots, we have here on the x-axis the 3D minus 1D from the southwest perspective, and on the y-axis and the northeast perspective. So if it's possible, if it's positive, and in this area, the top pixel is brighter in 3D than in 1D for the northeast, and same for the southwest if we look at the left section. And to also explain the one-to-one line, this means that we have no sun position effects and contributed mostly to the horizontal photon transport. So yeah, if both are negative, and to the same degree, we know that the sun position doesn't have an impact. And if we have a look at the 1 to -1 line, we can then assume in a simplified way that it can be contributed entirely to the cloud slope and illumination and shadowing effects. And here we can see now the results. So our reference is the southwest side, and we can see illuminated pixels indicated in reddish, and they are mostly on the positive side, but we can also see that some shadowy pixels are also on the positive side, and some illuminated pixels have a negative 3D minus 1D, so it cannot explain all. But what it can explain is that for almost all pixels, it is still brighter than it would have been if it's on the shadowy side from the northeast version. So even if it's negative, it's still brighter than it would be if it's on the shadowy side. And the other component can be explained by the horizontal photon transport. So again, the concept is shown on the right. So the positive values indicate that the pixel we're considering receives more photons from neighboring pixels than it gives, and opposite for the negative values. So as a proxy, we use the 9-pixel mean, so also the surrounding of the pixel we're considering, and use the difference to the reflectance. And here we can then see that brightening is stronger if the surrounding is brighter. So we can then explain our values that are before difficult to explain from the brightness temperature gradient with the horizontal photon transport. So yeah, the pixels shown here indicate, okay, we have here a negative slope, but we also get more photons from the neighboring pixels. So as a conclusion, the brightness temperature gradient cannot explain all of the 3D radiative effects, and we can still assume that generally illuminated slopes produce more positive values and shadowy slopes more negative values. Now we have a look at the observations. So what is the impact on the EarthCARE retrievals? And we use here as data the MSI products in the level 1, the RGR with 4 solar reflectances, 3 brightness temperature gradients, also the solar observational geometries, and calculate from that the brightness temperature gradient. And we also use cloud phase and the optical properties from the COP product. And we can also use, which is really nice from EarthCARE, we can also use the products from the other instruments. So in the study, we use Captivate, which is a synergy retrieval from the radar, LiDAR, and imager combination, which uses only the visible channel and from MSI. from the solar reflectances, and we also have the composite product, which combines the single instrument retrievers. Here we only consider pixels which use retrievers from radar and LiDAR to be independent from MSI. So now we first look at the level 1 and reflectances of pure ice clouds. And in this plot, we check the asymmetry. So here we have different bins on the x-axis of brightness, absolute brightness temperature gradient. So we combine here the illuminated and the shadowy. On the left, we have more of a low slope, and to the right, more of a high slope. And now we calculate the ratio of illuminated to shadowy counts within those bins. And we can see that for really high visible reflectances, also from the 1D perspective and unphysical reflectances, which reach here up to 1.2. For higher cloud slopes, almost entirely from the illuminated side. So here the plus indicating we don't have any shadowy pixel reaching those reflectances. And we can also use the composite product as a reference. So in this plot, we use the ice water path, assuming that thinner clouds produce lower reflectances and thicker clouds high reflectances. And here for our bins, so here on the top we have illuminated, into the bottom shadowy, and in the middle more homogeneous. And we can see if we follow one horizontal line, we can see that the reflectances increase from thinner to thicker cloud, but also increase from shadowy to illuminated, and also clear differences. So for same ice water path, we here have an average reflectance of 1.0 compared to the shadowy with a reflectance of 0.6. So high reflectances appear more on the illuminated side, and illuminated columns produce higher reflectances. Now, what is the impact on the microphysical properties? Now, first looking at optical thickness, and we can see that the signal gets replicated quite nice. So we have the same concept from left to right, from thinner to thicker, using the composite product as a reference, and again illuminated to shadowy. And here we calculate always the mean for each bin, and then the deviation from the bin. So here we can see that it's over 40 higher in the illuminated region. The effect clearly propagates into the cloud optical thickness, and we can also see the nonlinear relationship of reflectance to cloud optical thickness. So yeah, the effect on the illuminated side is therefore a bit stronger, but we can also see even for lower cloud slopes a clear effect of higher cloud optical thickness on illuminated side and lower on shadowy side. And we can see the opposite effect for effective radius. We use here the captivate product as at an optical depth of 1 as a reference. And again, the deviation from the column mean. And here we can see again clear biases on the illuminated and the shadowy sides. And for small brightness temperature gradients, the effect can be seen. And here I also want to mention that short-wave infrared reflectances, which are too low, often don't get accounted for in the EarthCARE retrievals. So we are also missing some values, which might explain why we have again here this this negative sign for shadowy pixels, which I did not expect, but the overall pattern is still in agreement with the findings. So yeah, we again have a propagation also into the effective radius. And yeah, we now also try to get a sign of the horizontal photon transport. I showed you with the proxy for the 1D perspective in the Monte Carlo simulations. So we don't have the 1D, but I just did it with the 3D, and then calculated the 9-pixel mean versus the visible. Yeah, so it's a bit speculative, but we still get the signal we expect. So to get lower effective radius if our pixel distributes more photons to neighboring pixels. But we can also see that we have negative values for the positive, and this indicates that the overall high variability within the 9 pixels leads to a lower effective radii. Now, the visible reflectances not only contribute to the imager retrievals, but also to the synergy retrievals. So then I wanted to investigate what is the impact on the synergy product from Captivate. And here we have a combination of the independent product, ACM-COM, so the composite product, using only the radar and the LiDAR, and the CAP product, which also uses the MSI. And here we again use the ice water path only from radar and LiDAR to be independent from solar reflectances. And here we can see the ratio. So assuming pixel levels of 1.0.8, we can then conclude it's 8% higher than it would have been if it was on a horizontal surface. So this is a case for 40 to 60 degree solar zenith angle, and yeah, we can see that the differences between the CAP and the COM product are at least partly controlled by MSI reflectances, and we can also see a propagation of the 3D radiative effects into the synergy product. And now switching to higher solar zenith angles, we can see that the effect increases, and we get a systematic bias for high cloud slopes or low cloud slopes, or yeah, roughly 10%. And yeah, so again, higher effect for lower sun. The summary, we saw that 3D radiative effects are structures. We saw the horizontal photon transport in the illumination and shadowing effects, and the brightness temperature gradient provides a simple proxy to diagnose the 3D radiative effects, but cannot be used as only proxy. So it's always a combination of all 3D radiative transfer effects. And yeah, the impact can then be seen also in the solar reflectances and the imager retrievals, and the radiances are used to improve the synergy, which they do. But yeah, for some cases we can also see then the propagation of the radiative effects into the synergy product. Yeah, this was my presentation. Thank you for listening, and if you have any questions, you can ask them now.